Okay, this is the final part of Chapter 4 for Dr. Sarkar's biochemistry textbook. So earlier we talked about the different types of our enzymes, and now we're going to get into a little bit more of the terminology, as well as some of the interesting stuff about enzymes that we need to know to kind of understand how they actually work. So, again, enzymes, reaction-specific biocatalyst. Remember what these all mean. The reaction, talking about a chemical reaction. Specific, meaning that one enzyme to one specific substrate go together. Bio, meaning that it's natural, it's in biology. Catalyst, meaning that it causes a reaction to occur quicker, typically in the sense that it lowers the activation energy or the energy needed for a reaction to take place. The substrate is what binds to the specific active substrate binding site on an enzyme. So if we have an enzyme, when the substrate comes in, there is a specific spot where it's going to actually want to go in and bind. When that spot is active meaning that it can accept a substrate, the active substrate binding site is where the substrate will gravitate towards and be able to actually bind. And we'll talk, there's some fun stuff that happens at that site as a result of substrate binding. Cofactors and coenzymes, those are chemical groups that are required for enzyme activity. So there are helpers, remember? The cofactors, coenzymes, remember factors. Fear factor is metal. The cofactors are our metals, our minerals. And our coenzymes are our vitamins. A lot of those, I think the B vitamins, if you remember, are mnemonic. Tall, rich nudists played pickleball for centuries. Remember, that's our B vitamins 1, 2, 3, 5, 6, 7, 9, and 12. Okay, and this is we're showing right here. We have specific binding sites that specifically fit the substrates that we want. That's what makes them specific. So we can have several different types of substrates, different stuff floating around, but the shape of that binding site is only going to fit the specific substrate that it wants to act on. Okay? So the enzyme substrate interactions, they're highly specific for their substances. The enzyme and its substrate must be complementary with their geometry, their stereospecificity, and also their charge distribution. Now so geometry is their shape. Stereospecificity, that is one of those words. I don't love that word. Let's see if we can get a better definition for it. So in chemistry, stereospecificity is the property of a reaction mechanism that leads to different stereoisomeric reaction products from different stereoisomeric reactants, or which again, stereoisomeric, that's a big word. Stereoisomerism or spatial isomerism. Now we're getting a little deeper. Isomerism, if we talked about the isomerase that we looked at earlier, right? It's saying the same chemical reaction but different configuration. So essentially the stereoisomer, what's the word? Stereospecificity, meaning that just because something has the specific chemical makeup does not mean that it can bind to that site. It has to also have the correct form, the way that it's bound. So for example, this enzyme here will bind dihydroxyacetone phosphate, but it won't necessarily always bind the glyceraldehyde 3-phosphate, which is kind of a bad example because this reaction can go both ways. But in other reactions, you'll see that it's specific to how everything is bound together and what its structure looks like in order for it to bind. And charge distribution. Remember, we have positive and negatively charged stuff, and the charges need to work out to be able to actually attract to one another. If they're not attracted correctly, then they're not going to ever bind. So like if a substrate is highly, highly negative and an enzyme is also highly, highly negative, they're not going to want to bind together. Okay. Thus, enzyme-substrate interaction is highly stereospecific. Enzyme-substrate binding are due to non-covalent forces, which include van der Waals, electrostatic, hydrogen bonding, and hydrophobic forces. Remember, hydrophobic means water-fearing, so they're trying to get away from water. Substrates that differ in shape and or interacting functional groups at the substrate binding site in the enzyme don't bind specifically. As a result, appropriate enzyme-substrate complex, meaning that when the enzyme and the substrate come together and bind, then they bind together, it's a complex, with proper energy content are not built, and the enzyme does not catalyze the reaction. So the conditions have to be perfect. So for example, here we go. We have, this is called the lock and key model, which is kind of showing how it works. So we have our enzyme and we have our active site. Our specific site, right there, is a specific shape. Now our substrate matches that specific shape. So the substrate will come and be attracted because of those non-covalent forces, the van der Waals, electrostatic, hydrogen bonding, and hydrophobic forces, and attach to that active site in the enzyme. So the enzyme changes shape slightly as the substrate binds. So remember when we talked about the shape of proteins, how the different amino acids and the way that it folded, or what amino acids were there, and like the charges of those amino acids determined how the protein was folded and what its shape was. Remember, an enzyme is a protein. So when you add a substrate to it, when you add more to it, bonds and interactions happen between the substrate and the enzyme. So you get what's called a conformational change. So you get a slight change in shape of the enzyme substrate complex when it binds. Okay? You can think of it like when if the substrate is that key, the key goes into the hole and it changes, like it'll push the different pins in the lock down, changing that shape. It's in order to allow you to actually turn that key. So once you have the enzyme, so the enzyme is going to do its deal. It's going to split that substrate into the different products, and then eventually it will release it. This is also the same thing that can happen if an enzyme is catalyzing a reaction in which it combines the two. Very similar, it's the exact same process, just rather than but it will have two active sites and two different substrates come in, and then it will change shape and bind them together, and you'll have that single product. Remember, at the end, what makes an enzyme is that at the end of the reaction, you're left with the exact same enzyme, that it does not get consumed during the process. So as we can see, we're left with the enzyme, and we have the products that come out. So enzyme substrate interaction and product formation. So lock and key method, breaking them apart, and then I got ahead of myself a little bit. This is how we get the combination of the two, right? So the function of enzymes as biocatalysts is to increase reaction rates. The reaction equilibrium is not affected. So here we have our enzyme where it'll come in. Enzyme, it binds that specific site. There's a conformational change. You can have things start to split up, and then you can get different products. In order to get different products, either you always have to add or you have to take away to get a different product. Otherwise, there's not a reaction actually taking place. Kinetics or collision theory for chemical reactions. So in order to react, molecules must collide, also known as being within the bond distance of one another. So this is actually why certain things increase the ability for reactions to occur. So for collision to result in a reaction, the reacting molecules must possess sufficient energy to overcome the energy barrier for the reaction. So a lot of the times when we talk about energy, we're talking about either chemical energy, we can also be talking about heat energy or movement energy. All of those kind of wrapped up are part of what we talk about with energy. So this is why if you've ever been in a chemistry lab, a lot of times when you want a reaction to occur, you heat up the solution, the liquid, whichever with the stuff inside of it. The reason why you heating it up gives more energy into the system, allowing for the reactions to take place. You think those molecules, when you add heat, the molecules move faster, making it more likely that they collide, and the more that they collide, the more likely reactions are to take place. So it's things like that that are going to determine the speed at which we can get those reactions. And that's why, again, the body has very specific requirements to maintain its balance or homeostasis, its balance. The pH level, the temperature, the amount of water, what minerals and what cofactors and coenzymes we have. That's why when we don't have those things, if our diet is deficient in those things, we can get sick. Okay, molecules must overcome energy barriers for a reaction. Earlier we saw that graph, how you need activation energy in order for a reaction to occur. And then, of course, our enzymes are going to actually lower that activation energy to make it easier on us. Okay, but the energy barrier exists between the substrate and the product. Energy is needed to align the reacting groups, formation of transient unstable charges, bond rearrangement, and transformation. So the molecules must be activated to a higher energy level for reactions. They have to go from this level to that level without a catalyst, without an enzyme, or to this level with an enzyme. And this is when we get into something that's called free energy, or Gibbs free energy, which changes during the process of chemical reactions. So formation of transient state and the decay of transient state to the product is linked to discrete free energy change. So forming the intermediate, forming the in-between state, and also then the breaking apart of stuff or putting stuff together, is due to it will change the amount of energy around them. We say if you're looking at, let's say, a cell itself, an enclosed area, that you can say that is a system, or with a certain space within which protein, an enzyme, and a substrates are interacting with each other, you can say, okay, that is a system. It's just kind of an easy way to say this space. Okay, and so when we talk about a system, it's just referring to a space with that stuff inside of it. So thermodynamically, thermodynamics, we're talking about temperature and changes of temperature, essentially changes of temperature and changes of energy, heat being defined as energy, or energy being defined as heat in this case. So thermodynamically, free energy is defined as the energy content in a system, remember that system is that space, that can be converted to do work at a constant temperature and pressure. It is useful energy, meaning that it can do stuff. It is denoted as Gibbs free energy, or big G. Every compound contains its own free energy content. So it has a potential energy. Every single chemical bond has energy inside of it, and when we break those bonds, we typically release energy, and when we form bonds, we typically absorb and take in energy. Normally, the energy content of a molecule not participating in chemical reaction is present in its ground state. The reactant molecule, or the substrate, S, is activated by means of supplying chemical energy, heat, or pressure. So all of these, remember, it's kind of the same thing. So if we add chemical energy, which you can add in forms of other chemicals, heat, so heating something up, or pressure, squeezing something, if you think an ice cube, If you go and take an ice cube out of your freezer right now and you hold it just like this, it'll start to melt because of the heat in your hand. If you squeeze it and apply pressure, that actually increases the melting process. It makes it go faster. And that's because increasing pressure also increases the amount of energy going into it, which will cause the ice to melt. So the substrate gradually gains energy and reaches its threshold limits in the transition state, after which the substrate is transformed to form a product. So once we get to that energy level, as we keep putting in energy, once we get to it, it transitions to the product. So what is the transition state, kind of in between substrate and product? A substrate compound is made up with chemical bonds that hold the entire compound and gives it a specific chemical property. As the compound is activated, it starts to gain energy. The electrons making these bonds are excited and start to vibrate within their limits. The electrons start to vibrate. If the energy supplied is higher than this limit, the electrons holding the bond are far more apart and the bonds start to break, making a transition state of the molecule. So the molecules, the electrons vibrate, get a little further away. The more energy you put into them, they're vibrating, and it weakens that bond to allow separation. At the same time, new bonds are formed as well. New charge distributions also occur to make new products in the transition state, and finally, a new product is produced. It's a lot of fancy mumbo-jumbo type talk. The overall thing is you have a substrate, you add energy to the substrate, the electrons vibrate, and then it causes them to separate into two products. So or two or more products, I should say. The ground state energy of the substrate is higher than the ground state energy of the product. So the substrate, because the substrate typically has more bonds in it, it's going to have higher Gibbs energy, potential energy, right, than of the product. So as the product has less bonds, so each product individually is going to have less available possible energy to it. The difference in the ground state energy between the substrate and the product is delta G. It can be written as G1 minus G2 equals delta G. And this is what we'll talk about. Whether delta G is positive or negative, we can determine whether or not a reaction is exothermic or I think it's exogonic. I think is the words that he likes to use. Let me double check that. Exergonic, sorry. Yeah. Exergonic. And endothermic or endogonic. Saying the same thing. Free energy change in standard conditions. So this is a bunch of sciencey mumbo jumbo. Like this is what we determine to be what the reaction is denoted by delta G prime 0. The difference between the ground state of the transition is called activation energy. We've mentioned that a couple of times. Activation energy of the substrate and product is denoted as delta G with the pluses. The figure shows a diagram where the substrate is producing a product. As the substrate is gaining energy, it is going to its transition state threshold limit. So right there, that's its threshold limit. After which gaining of a little more energy would break the bonds of the substrate and produce products with lower ground level energy. So see how it goes up and then it goes down. Hence the standard free energy change in this reaction where S is forming P is negative. So see how this right here, we've actually, from substrate to products, we've lost energy in the actual chemicals themselves. What does that mean about the surrounding area, though? Because energy, if we think about some of the big sciencey laws, is that energy cannot be created or destroyed, only transformed. So it was chemical energy in the form of bonds. When those bonds get broken and it goes out into a system, and we have a negative delta G, we're talking about an exothermic reaction, or that energy is being released in the form of heat. Hence, the standard free energy change in this reaction where S forming P is negative, i.e. the reaction is exergonic, at equilibrium and favorable. Exergonic reactions are favorable, meaning that they're more likely to occur than endergonic or endothermic reactions. Note here, the required activation energy for the product is higher than the activation energy of the substrate to reach the transition state. So if we want to go backwards from product to substrate, it's going to require a lot more energy, and we're actually going to end up with a positive Gibbs free energy, a positive delta G. And the positive delta G is going to be our endothermic reaction, or endogonic. Endo or ender, I don't know, something like that. You'll see it in the book or in his slides or when he talks about it. I learned it as endothermic, but he prefers the terminology of the gonic. So note here that the required energy is higher to reach the transition state, hence it would require more energy to reverse the process. More details about free energy and thermodynamics concepts about free energy are discussed in the bioenergetics section, which is later on. The formation of transition state and the decay of transition state of the product is linked to discrete free energy change. So a very simple way to remember this is that if you have a negative delta G, energy goes out. Exergonic means it gets hot. A positive delta G equals energy goes into the reaction. It is an ender or endogonic, I don't remember which one, endogonic, and it's going to feel cold. So when you touch it, it's going to feel cold. So it's kind of like exergonic reaction would be like combustion in a car. When you burn gas, it gets hot, and that's a exergonic reaction. That's why if you touch the engine after it's been running, it's really, really hot. A positive delta G is something like they're like instant cold packs. I don't know if you've seen those where if you pop them, just like there's instant hot packs, instant cold packs where you can pop them and it'll like turn to a gel and it gets super, super cold. And that's because there's an endothermic reaction occurring. The reaction is actually taking in all of the heat around it to get cold. It's kind of cool. Role of enzymes in biochemical reactions. We've talked about this a lot already, but let's go. Enzymes increase rate of chemical reactions by decreasing activation energy. So decreasing that activation energy. This is one of the most important things to remember right here. I don't know why it won't let me highlight. Let's see if it let me. There we go. The difference between the energy levels of the ground state and the transition state is the activation energy. So remember, we're talking ground state to transition state to get it up to this point, to get those electrons vibrating, to get them to start to separate. Reaction rates can be enhanced by increasing the temperature and or pressure. We talked about that. Thereby, increasing the number of molecules with sufficient energy would overcome the energy barrier. The activation energy can be lowered by adding a catalyst. And so this right here, this is the whole reason why we need catalysts. We have a limited amount of energy in our bodies, and we want these reactions to take place smoothly. So by adding catalysts, it's easier for our body, and it requires less energy to perform the reactions that it needs to. Role of binding energy in enzyme catalysis. To decrease the activation energy for a reaction. Actually, this just reminded me of something that we'll talk about a little bit. So it's anabolic versus catabolic reactions. Make sure we get it good. I think it's in this section that he talks about this, but we'll have to see. So anabolic, you use energy to build complex molecules, right? Building it up, putting them things together. Catabolic breaks down. So think if you've ever heard of like anabolic steroids. Anabolic steroids is to build muscle. Catabolic, cats are kind of chaotic. They really like to break stuff down. Again, stupid ways to remember things, but whatever works. So we look at anabolic. If we're building, if we're putting stuff together, is that going to be an exergonic or an endergonic reaction? Does it put energy out or bring energy in? In order to form new bonds, it brings energy in. So anabolic reactions are going to be endothermic or endergonic. Catabolic reactions are going to be exothermic or exergonic. Okay? So the role of the bioenergy enzyme catalysis. To decrease the activation energy for reaction, the system must acquire an amount of energy equivalent to the amount by which free energy change during uncatalyzed reaction is lowered. Much of this energy comes from binding energy contributed by formation of weak non-covalent interactions between substrate and enzyme in the transition state. Woo. Just another chart just kind of talking about all of this stuff. We've already talked about pretty much everything here on this chart. This is showing that when you bind the enzyme catalyzed reaction, when you bind here, you get a much lower transition state. So now you need a far less energy to get the reaction to happen. Enzyme substrate interaction. Enzyme substrate interaction. Functional groups of the enzyme and substrates interact and lower the activation energy. They may form transient covalent bonds, may transiently transfer a group from the substrate to the enzyme. Non-covalent interactions generate binding energy and used to build catalytic power of enzymes. A lot of this is kind of a little bit above our pay grade. Don't worry too much about this. Just understanding like what the enzymes actually do in the formation of the products. Catalytic strategies. Proper positioning of the functional groups, acid-base catalysis. We have covalent catalysis, metal ion catalysis. So it's just kind of talking about those different ways that the reactions can occur. Enzyme kinematics, study of chemical reactions catalyzed by enzymes. So the effects of S. Gradual increase in S, those little brackets mean concentration of substrate, increases reaction velocity. So if we add more of our substrate into the system, right? Let's say we have a glass vial, that'll be our system. We add more of the substrate in, and there's enzymes in there. Remember, the reaction occurring is based on things knocking into each other. So if you add more of it, more likely a reaction is going to occur. So that increases our reaction velocity. Okay? So it increases how quickly it happens until the enzyme is saturated, meaning that until all of the enzymes that we have available are full, until they are able to finish breaking down stuff, releasing the products, and then are then open again for the next substrate. But they all of them get full, all of them have substrate on them, and they're all working on breaking it down. And that's why you get a plateau where you eventually get your V max, which is the maximum amount of substrate that the maximum amount of substrate that amount of enzyme can consistently break down during a period of time. Lots of fun. This graph, you will have quite a few questions on this graph. It is heavily hit on as well in boards. So this is a good one to really go watch a couple of YouTube videos on this one. There's some by Ninja Nerd and then Khan Academy as well. Have some really, really good ones to observe and to understand this a little bit better. Enzyme catalyzed reaction. Let us consider a chemical reaction in which a substrate is producing a product. The enzyme catalyzed this reaction is E. At equilibrium, we can write the reaction equation as S to P, or also P can go to S. Now, if the rate constant of forward reaction is K, the rate constant of forward reaction is K1. So that means rate constant, so the rate at which that reaction is occurring in the S to P direction, okay? Meaning that the substrates are being turned into products. And the rate constant of the backward reaction is K2. So the rate at which constantly, P is being converted back to S. So the products are being converted back to the substrate. Then the equilibrium constant for this reaction is described as KEQ. At standard condition, so at standard condition, we're talking about a certain degree Kelvin, the specific atmospheric pressure, the specific pH, all of that good stuff. It can be written as KEQ, K little eq. And that depends on the concentration of the products formed and the reactants used. Thus, KEQ equals concentration of the products divided by concentration of the substrate. From the thermodynamic point of view, at standard conditions, we can relate that delta G prime with KEQ as delta G prime equals negative RT, and then the natural log of KEQ. This is a lot of math stuff. We'll go into this a little bit, but not a whole lot. And so several of these are constant, right? So at the standard conditions, if we have standard conditions, R is a constant, so we plug in 8.315 joules per mole into R. T is the absolute temperature of 298 Kelvin, so we'll plug that in for T. So then the only things that we're looking for, either we're looking for that delta G or we're looking for the KEQ. Okay? And you won't really be responsible for doing a lot or any math in this course. So don't worry too much about know the equation itself and what the equation represents, but you don't necessarily know how to actually solve this for the stuff. Now for reaction S to substrate to product, the rate or velocity of the reaction, V, so V being the velocity, represents the amount of S that reacts per unit time. The rate equation is thus V equals Ks. K is going to be another constant. This indicates rate is directly related to the substrate concentration. So this is the key that you want to get from here. The rate is directly related to the substrate concentration. Okay? Then now we're going to keep getting into more math, more constants. So a lot of this starts to get a little bit complicated. There's a lot to it. I highly recommend that with the equilibrium constant stuff, jump over to Ninja Nerd. And I'm pretty sure he has a specific equilibrium constant. So Ninja Nerd, you can see all the Ninja Nerd that I've watched in my day. And if we talk about biochemistry equilibrium. Bam. Michaelis-Menten equation explained right there. Just what we have here. And he'll do a really good deep dive into what this all is, how it all works out, why it works out the way it is. Again, I love his videos. Really good for understanding these topics at a much deeper level. And he'll go over, you can see and go through a lot of this as well. Don't get too hung up by these graphs. If you find a good YouTube video on them that helps walk you through them, it's really helpful. I'm not going to walk through it just because I don't have a mastery of this subject. And so I don't want to try and explain all of it to you guys and run the risk of saying something incorrectly or confusing you. So I will leave that to the experts, the masters of this material. Okay. This is a really long chapter. As an enzyme catalyzed reaction proceeds, more products are produced as the substrate concentration decreases up to a certain time. Therefore, as the substrate concentration diminishes or exhausted product formation produces a plateau, i.e. there's no more synthesis of the product. It is for an enzymatic assay to determine the time at which this plateau is reached. So assay being a different scientist. This gives us the idea to determine the time optimum for enzymatic reactions. So what time we should give them for these reactions to occur. What else do we have in here? Man. So this is a really, really long chapter. Let's get through the last little bit of this. Okay, units of enzyme activity and specific activity. Again, this is just talking about the units, the enzyme activity, specific activity, kind of the concentrations, units that you'll use, effects of pH. Enzymes have their own specific pH. If you don't have the optimum pH, the reactions do not take place. We've said that quite a few times, right? So there needs to be certain pHs. Pepsin is one of your enzymes found in the stomach that digests proteins. It needs a really, really low pH. Glucose 6-phosphate needs a much higher pH because that's in our normal cells. So stomach versus the actual cells, they need different pHs in order to function. There's a little bit of overlap. That's why you see there is a big window here, but overall our body you need specific pHs for specific areas of the body. Temperature optima for enzymes. You need a good temperature. That's why body temperature is great. But extremes of temperature, so like boiling, denatures enzyme proteins, means that it breaks them all the way apart. So then your body can't do what it needs to do. If it gets too cold, they can't do what they need to do. Inhibition of enzyme activity. So this is our unit of stopping the enzyme. How do we control the enzymes, right? There's two different types. We can talk about reversible, meaning that you can undo it, and irreversible, meaning that once it's bound and inhibited and stopped, it can never be broken up, and that enzyme just is worthless. We have competitive, uncompetitive, or mixed or non-competitive. Okay? Competitive inhibition. Essentially what competitive inhibition is that you have a competitive inhibitor, which is going to be a similar... Sorry, one sec. Cat likes to play in the dirt. The competitive inhibitor is going to be a substrate that has a similar shape to a difference of an inhibitory substrate that's going to have, or you can just call it, there's a competitive inhibitor, which is another thing that's similarly shaped to the substrate itself, and it can prevent the substrate from binding to the enzyme. So it's going to directly compete with the substrate itself for the spot of the active binding site on the enzyme. Okay. Here's the chart for the competitive inhibitor, how it changes. This is knowing these are really, really good test questions of where, okay, if you add in a competitive inhibitor, what happens to the velocity of the reaction? And in this case, this is our normal, and we get a slowed down reaction time because we have less enzyme available to bind. Uncompetitive, I think they'll also call this allosteric. Let me double check on that. Yeah, allosteric inhibition is the other name for it. So uncompetitive, aka allosteric inhibition, you will have a secondary inhibitor, an uncompetitive inhibitor, affecting the enzyme's catalytic function but not the substrate binding. So uncompetitive inhibitor binds at a separate site on the enzyme and only to the enzyme substrate complex but not to the free enzyme. So it only binds to the enzyme substrate complex after the substrate is bound. So essentially it's going to bind there and it's going to lock in the substrate. So it's going to lock it in so that way it can't finish breaking that substrate into products and releasing it. So essentially it's going to put a pause on the enzyme. In the process of the uncompetitive inhibitor, the Michaelis-Menten equation is written as right here. So you'll see a lot of this is the Vmax and the Km. These are the kind of details you want to know. And like I said, watch those videos on understanding these equations, because they just do such a much better job of me explaining this kind of and how that process works. Mixed or non-competitive inhibition. Mixed inhibitor binds at a separate site, but may bind to either the empty enzyme or the enzyme complex. Okay, so we can do bind on either. Non-competitive inhibition, here are the charts for these. Spend a little time on those. And this, honestly, this table right here, if you can memorize this table of what happens with each one, whether the Vmax, what happens to the Vmax, what happens to the Km, if it decreases unchanged or whatever, if you can memorize this, that's test questions right there. That's how he's going to word a lot of these questions. Okay, we talked about reversible, now we're talking about irreversible inhibition. So in this case, irreversible inhibitors form a covalent linkage with the required functional group in the active site of the enzyme, or form a partially pretty stable non-covalent linkage. So either covalent linkage or non-stable linkage, but that it's pretty stable. Thus, enzymes become completely inactive. For example, aspirin irreversibly inhibits the cyclooxygenase enzyme. That's going to have to do with your COX system. This is for your inflammatory system. Stuff like allergies and stuff, pain, was for your COX system, your cyclooxygenase system. It produces eicosanoids. You'll learn more about eicosanoids in Biochem 2. The COX enzyme contains a serine residue hydroxyl group at its active substrate binding site. A lot of words. This serine hydroxyl group is acetylated permanently by aspirin, and COX oxygenase is irreversibly inhibited. So what you want to take from this, aspirin blocks the cyclooxygenase because of acetylation. And also heavy metals, lead, calcium, mercury, sulfhydryl groups, all of those are going to cause irreversible inhibition. So that's why lead poisoning is so serious, or if you take way too much calcium, it can also be really, really bad. Mechanism of regulation of enzyme activities: allosteric regulation, negative feedback, feed-forward, tissue-specific isoenzymes, alteration of the active substrate binding site, regulation of enzyme concentration, regulation of substrate and product. So all these are ways that they are going to control that regulation. If you don't understand any of these, give them a quick Google search and write that definition right here next to them, because I promise you a lot of this will come back, and there'll be a couple of test questions, something like, which of the following is not a mechanism of regulation of enzyme activities, or which of the following are mechanisms of regulation of enzyme activities. Regulation through conformational changes of the enzyme do not affect enzyme concentration. So the amount of enzyme does not change, just that the amount of enzymes that are actually working changes. So you can have the allosteric modification by regulatory compounds. Allosteric modification, essentially what it means is that you have some form of metabolite and or cofactor or something. They come and they bind to a secondary site on the enzyme, which then changes the shape of the enzyme, no longer allowing more substrate to continue to bind, for the protein to continue, for the enzyme to continue to break down substrate. Okay. Protein-protein interactions, we talked about this already a little bit before. Okay, I'm gonna make a correction to what I said earlier. Don't think of uncompetitive as allosteric. I'm gonna go ahead and delete that. Think of allosteric as its own thing. Okay. So I apologize for that. So allosteric, when you have binding, it can do a couple things. Hey, sorry, give me one moment. she's deciding to be a little pain today. It's okay. So, allosteric enzyme changes its conformation. So, allosteric, allosteric is when something else will bind to it to cause a conformational change in the enzyme. So, this can actually be positive or negative, being that you can have something bind, you can have a positive or a negative modulator. So something like, we talk about hemoglobin. Hemoglobin has 4 potential binding sites for oxygen, and when one oxygen binds, there will be a conformational change to the whole thing, opening the second binding site for another oxygen. When that oxygen binds, it opens up, it changes again to allow for a third oxygen, and then again for a fourth oxygen. So that would be an example of a positive modulator for this. Okay, when a positive modulator binds at the regulatory site of the inactive enzyme, a conformational change, so the shape changes, occurs the enzyme favoring substrate binding. The enzyme is now activated. This enables substrate to fit, bind, and interact at the catalytic binding site of the enzyme. When a negative modulator binds to the enzyme's regulatory binding site. So now we've talked about positive, now we're talking about negative modulator. The changes in conformation does not favor substrate binding or decreases the substrate binding, thereby either completely or partially stops enzyme activity. In this case, the modulators bind at a different site other than the substrate binding site of the enzyme, and changes to conformation of the enzyme accordingly either to activate by a positive modulator or to inactivate by a negative modulator the enzyme activity. The binding of modulators are reversible. Often this type of modulators are known as allosteric or different site regulators. Regulation by metabolite. So this is going to give you more of the of some of those regulations that we talked about all in here. I'm not going to go through all of them just for sake of time. But no, so all of these, go through each of these and just take a look at the picture, figure out what's happening. Again, if you're a little bit lost, do a quick Google search, quick video. These individual reactions shouldn't take you more than 2 or 3 minutes to look at each one. Regulation by protein to protein interaction. Calcium chemodulin complex binds to calcium chemodulin dependent protein kinase and activates it. So you'll have a protein binding to a protein to activate it. That's another way. We'll get into some more of those reactions later on. Regulation by proteolytic cleavage, so breaking something apart. So chymotrypsinogen to chymotrypsin makes turns active, or trypsinogen is the inactive form, and then it gets broken into trypsin as the active form. So the proteins will get broken down, parts will get cleaved off, and to activate it. And that is all of chapter 4. It's a big chapter. Enzyme activity, though, is really, really important. Again, just from this video, good things to know. Make sure you go back, watch a video or something on this stuff. This will be on boards. This chart right here, very, very important. Understanding the different types of irreversible versus reversible inhibition, and then also look through this again to understand the allosteric, the different regulations of enzymes. Thank you so much for watching. Have a great day. Good luck studying, and good luck on everything that you have to do today. And I'm tired already. It's 9 in the morning, and I'm already a little bit tired. Well, we'll get through this. Have a good day, everybody. Bye.